this point. Okay. So this is number 9 in chapter 5 of Shear and Levy. Okay. Let's say that we have just the following initial value problem. Okay. So this is still a parabolic equation. Okay. But we're just going to show how the fundamental solution can be extended to handle problems beyond just the heat equation, okay? And so in this case, you have this thing D, okay? D is a constant, okay? And it's greater than 0, okay? And we'll also say that G is integrable, okay? And let's say it's continuous as well. Okay. So this will just be kind of a plug and chug. So so for part A, let's say that we want to solve this problem. Whenever you have parabolic problems like this, and this is common also in hyperbolic problems, one way to approach them is just to turn them into the canonical equation, or that class of problems using a change of variables. Okay, and this will come up again and again, both in linear and nonlinear PDEs. Finding the right change of variables. How do you know what's the right change of variables? Well, some of that comes with experience or working on sort of similar problems, knowing something about what happens with the product rule. Okay, now, there is a change of variables that will turn this into the heat equation. Okay, so let's use the following change of variables to show that we can turn this into the heat equation. So let's say U is equal to e to the minus dt times v of xt, okay? To find an equation for v of xt, okay? That's the first part of this problem. So they'll give you some practice doing changes of variables.
With all these little d's floating around, I was afraid that they were differential elements.
Oh,
and I was like, how do we solve this?
I know it's a bad constant, but yeah, that's what they use. But no, it's supposed to be a constant. Okay. Should hopefully be like two lines of calculation. All right. Well, I'll just go through it because it's pretty quick. So if we plug this in, right, to our PDE, then we have that u sub t plus du. Now, is equal to minus d e to the minus dt v, right? First part of the product rule there, plus e to the minus dt v sub t plus d e to the minus dt v is equal to, and then it's straightforward here because e to the minus dt does not involve x at all. We just get e to the minus dt v sub xx, right? Because this is what, sorry, k u sub xx should be. So I have an extra k living out there, okay? So this is my left-hand side, right? And this is my right-hand side now, okay? And I can cancel these parts out. And I can also divide through by e to the minus dt, and I get just v sub t equals k vxx, okay? So as foreshadowed, I just get back that v, which is a new variable now, satisfies the heat equation, right? If I want to solve this initial value problem, what's one more thing that I have to do to set up the initial value problem?
You need the initial conditions.
Right. Yeah. So what's the initial condition now? So what's v of x0 going to be?
Just u of x0.
Yep. Yeah, because t0, this thing is just 1, right? So I get e to the d0 u of x0. So I just get u of x0. So I just get g of x. Okay. Easy mistake to make, though, is when you do these change of variables, don't forget to make sure and adapt your initial condition. Okay. All right. So now what is v? So part B will be solve. Right. What's v going to be in this case? And you can say it in terms of the fundamental solution.
Convolution of the fundamental solution in g of x.
That's it. Yeah. Phi convolve with g, right? Which we can write out, more generally as phi of x minus y t g of y dy. Okay. So now what is u of xt?
Just that times e to the minus dt.
That's it. All right. So this is going to prompt an additional question. G of y dy. Sorry, that's sort of smushed over there. Okay. So let's rewrite that in the next page, right? So u of xt is equal to e to the minus dt integral from minus infinity to infinity, phi of x minus yt, g of y dy. Okay. So that's our solution, right? What were the steps? Change variables, solve the initial value problem in the changed variable, change variables back, right? Don't forget to change variables back when you use a technique like this, right? Okay. So this is interesting, right? It looks a lot like the heat equation solution, but now it's got this extra term hanging around, okay? And so if I had to ask you sort of give me a physical interpretation now for what this additional term is doing, what would you say is happening? Let's say if d is greater than 0, what's happening to the heat in the system over time?
Like a